Hi, my name is Filippo Bianchi, and I'm going to discuss the total variation GNN, which we presented at the ICML 2023. Traditional clustering approaches mainly follow two strategies. The first is to cluster samples by looking at their feature. The second is to first build a graph whose topology represents the similarity between the features. Then we partition the graph into groups of strongly connected components, which represent the clusters. Note that in this case, the graph is built from the feature of its nodes. But what happens if the graph is given in addition to the node features and it carries an additional information? In this case, we talk of attributed graphs, where the topology and the vertex feature can carry different information. Methods for clustering based on graph neural networks are able to account for both the topology and the node features when computing the clusters. This gives them more flexibility compared to traditional clustering methods. Now let's look in detail into the common framework used to perform clustering with a graph neural network. We usually have a stack of message passing layers which take in input the topology represented by an adjacency matrix A and the node features represented by a matrix X. The stack of message passing layers generates new node features, also called embeddings, by applying a linear transformation and by combining the information of the neighboring nodes on the graph. Importantly, every message passing layer performs a smoothing operation of the node features, since every time the features of a node are combined with its neighbors, they become locally smooth on the graph, meaning that neighboring nodes end up having the same features. Finally, the node embeddings, which are the node feature generated by the last message passing layer, are fed into a multi-layer perceptron, which computes the soft cluster assignments represented by a matrix S. So how does the matrix S look like? It is a matrix where every row indicates the membership of each node to the different clusters. For example, this entry indicates that vertex 1 has a membership of 0.7 to cluster 3. Clearly, the amount of membership is limited and is the same for each node, meaning that each row in S must sum to 1. The soft cluster assignments already accounts for the node feature, but that is not enough. It is also necessary to have an auxiliary loss that encourages the formation of a good cluster partition on the graph. For this purpose, one can look at the minimum cut, which is the task of partitioning the graph in k disconnected components by cutting as few edges as possible. The minimum cut is defined according to this particular optimization problem. To understand the components of the objective function, let us consider this simple graph, where we apply the following cuts depicted by the blue dashed lines. The line on the top cuts 3 edges, while the line on the bottom cuts only 1 edge. The numerator in the loss function counts the total number of edges that are cut. Clearly, we want to form cluster by cutting as less edges possible. So a better solution would be this one, where we cut only 2 edges. But this is also a solution that cuts only 2 edges. In this latter case, however, the clusters that we obtain are value imbalanced since 2 of them contain only 1 node. So how can we be sure to select the first one? This responsibility is left to the denominator in the loss function, which penalizes the more unbalanced partition among those that cut the same number of edges. So we have all that we need to generate good partition, but the problem is that this is a discrete optimization problem, and finding a solution for this has a combinatorial complexity. The common way of addressing this issue is to apply a continuous relaxation and recast the discrete optimization problem into a continuous optimization problem. In particular, partial clustering changes the problem in this way. The cluster assignments to be optimized are no longer discrete, but they are real valued vectors in Rn. Let's now take a closer look at the two terms in the loss function of spectral clustering. First, we have the denominator in blue, which measures the local quadratic variation of the cluster assignments. Basically, it measures how much nodes that are connected on the graph ends up with the same soft cluster assignments. Having this term in the loss ensures that cluster assignments S are smooth on the graph. Importantly, this is very compatible with the method passing operation that ensures that node fetch features X are smooth on the graph. Indeed, the cluster assignments S are computed from the node features, so there is a synergy in encouraging both of them to be smooth. On the other hand, the denominator of the loss function in spectral clustering is the continuous relaxation of the balancing term that we saw before. This term can be implemented in several different ways, resulting in algorithms that give slightly different results. But in any case, the term always ensures that clusters are balanced. And this helps to prevent the two most typical degenerate solutions. The first is when all nodes end up being assigned to the same cluster. And the second is when all nodes are uniformly assigned to all clusters with the same membership. Two prominent examples of GNN-based approach that use an auxiliary loss inspired by spectral clustering are min-cut pool and daemon pool. Both methods define a loss that contains a local quadratic variation term, which ensures that neighboring nodes on the graph are assigned to the same cluster. And there is also a balance term that discords the degenerate solutions. So what are the pros and cons of spectral clustering? Well, the pros is that spectral clustering is a robust and well-established framework to approximate the optimal minimum cut solution. And perhaps most importantly, spectral clustering allows to compute the solution of the relaxed optimization problem in a closed form way when the balancing term is defined in certain ways. However, having a closed form solution is not so important in a neural network framework, since we are anyway optimizing the neural network with gradient descent. And therefore, we are not really exploiting the fact that we have an analytic solution for optimizing some of its part. On the other hand, and here are the cons, spectral clustering has an important weakness, which is that the approximation error due to the continuous relaxation that we saw before can be arbitrarily large. Either relaxation of the minimum cut problem replace the quadratic variation term at the numerator with a graph total variation term, which is the sum of the absolute value of the differences between the assignments of adjacent nodes in the graph rather than the square differences. This relaxation is tighter in the sense that it gives a better approximation of the optimal minimum cut. Importantly, since the graph total variation involves the minimization of an L1 norm, the soft cluster assignments that one obtains are much sharper. This makes a difference, especially in the nodes close to the edge of a cluster, like in this figure where on the top of each node, we show how soft cluster assignments look like, while in the bottom, we have the ideal cluster assignments that are sharp. Very smooth cluster assignments reflect the uncertainty to which cluster a node actually belongs to. For example, the nodes at the edges are only 60% sure to belong to their actual cluster. We are finally ready to introduce the proposed total variation graph neural network, which consists of two main ingredients. The first is a new loss function, which is an adaptation of the asymmetric Kiger cut. The original formulation consists of a ratio between the graph total variation and the cluster assignments and a balancing term. However, having such a ratio within a loss used to train a neural network is not a good idea, since it can create numerical instability during training. especially when the denominator approaches zero in the proximity of the general solution, which is something that often occurs at the beginning of the optimization procedure. To address this issue, we take a linear combination of the two terms rather than the ratio. Then we introduce normalization coefficients to ensure that both terms take value within the interval 0, 1. And finally, we add the weighting coefficient to control the contribution of each one of the two terms. The loss we obtain is now numerically stable, and since the terms take value in a control range, it is also easy to combine it with other losses, such as a cross entropy when performing a task such as graph classification. The second ingredient is a new message passing layer. So why do we need it to start with? The problem is that on the one hand, we want to minimize the graph total variation of the cluster assignments, which involves the minimization of NL1 norm, as we saw before. On the other hand, we have the standard message passing layers that instead minimize the local quadratic variation of the node feature, which involve the minimization of NL2 norm. This clearly clash. There is clearly a clash between these two optimization objectives. What do we want is a message passing layer that minimizes the graph total variation of the node feature, not the local quadratic variation. So how do we do it? First, we compute the derivative of the graph total variation of the node feature. Based on the derivative, we define an operator, L gamma of t, that takes a gradient step of size delta towards the minimization of the graph total variation of the node feature. Finally, we transform the node features with trainable parameters, and we had a nonlinearity, obtaining in this way a full-fledged message passing layer. Some remarks about the operator L gamma of t. It is actually a combinatorial Laplacian, where D is a degree matrix and gamma of t is an operator that matches the same sparsity pattern of the adjacency matrix. In particular, the entry ij of gamma of t is given by the ratio between the entry ij of the adjacency matrix and the L1 norm of the difference between the features that are on node I and node j. Also note the superscript t, which indicates the dependency from the node features obtained at step t. Since the features x of t change from layer to layer during training, this means that edge weights described by the operator gamma of t are trainable, and therefore they can be adapted during training. Now that we have defined the GTV-conv layer, let's take a closer look at what happens to the node feature. Each time they go through a GTV-conv layer, their graph total variation change. In particular, each GTV-conv layer reduces the graph total variation by taking a gradient step of size delta. The more layers we had, the more the graph total variation is reduced. So this is how the final GNN model looks like. The standard message passing layers are now replaced with the GTV-conv layers. In our work, we consider two downstream tasks. The first is node clustering. Here, there is only one graph, and the goal is to assign to the same cluster nodes whose features are similar and that are well connected on the graph. The architecture we use for this task is very simple and consists in a stack of GTV-conv layers, which generates the node embeddings, followed by an MLP layer that computes the cluster assignments. Note that clustering is an unsupervised task, and that architecture is trained only by minimizing the proposed auxiliary loss, which is also unsupervised. The second task is graph classification, where we have multiple graphs, and the goal is to assign each one to a label representing its class. Compared to node clustering, now we also have a pooling operation that computes a coarsened version of the adjacency matrix and the node features, respectively A pool and X pool. Since graph classification is a supervised task, this GNN architecture is trained by minimizing also the supervised cross entropy, in addition to the unsupervised auxiliary losses. Also note that we have an auxiliary loss for each pooling layer here. Let's start by discussing the results on the nodes clustering of the popular citation network Cora. Among the methods compared in the paper, we consider the three main competitors, which are diff pool, min-cut pool, and daemon pool. First, these plots that are here, I'm showing here, represent the node feature generated by the last message passing layer in the 4 GNN models. Those are the features XL that are fed to the MLP to generate the cluster assignments. Clearly, if they are well separated, also the cluster assignments will be separated. For visualization, the node features are projected in only 2 dimensions using the UMAP algorithm and are colored according to the cluster assignments. We see that our method produces clusters that are compact and well separated. Next, we color the same data according now to the true class labels rather than the cluster assignments. In the other GNN models, the classes are all mixed up in the different cluster. On the other hand, TVGNN produces a much better correspondence between the clusters and the actual 7 classes. Finally, we visualize the matrix SS transpose. Remember that S is the soft cluster assignment matrix. If the cluster assignments are sharp, we see a block diagonal structure in SS transpose. For diff pool, the cluster assignments are extremely smooth. Basically, we have a situation like this where we have that every node is assigned uniformly to all clusters. For min-cut pool and daemon pool, we see a block structure, but there are also non-zero elements in the off diagonal. This is because while the assignments are sharp at the center of a cluster, they tend to be smooth at the cluster edge, probably because there is some overlap, which indicates that the clusters are not well separated. Finally, the cluster assignments generated by TVGNN are very sharp everywhere, since all the off-diagonal entries in SS transpose are 0. This indicates that the clusters are well separated. As a remark, by looking at the number and size of the diagonal blocks, we can see that both min-cut pool and TVGNN identify 7 distinct clusters, which is the number of classes in Cora. On the other hand, diff pool finds only 1 big cluster, and daemon finds 6, but one of them is very small. To better show the problem of soft transition between clusters, let us consider an example on a simple point cloud, which we ask to partition in 5 different clusters. The transparency of the color indicates the maximum value of the cluster assignments of each node. In this pool, everything is very transparent, since the highest cluster membership is always low. Also, the cluster assignments are generally broken and not very consistent with the graph structure. In min-cut pool and daemon pool, things look pretty much okay, but if we look closer, we see that the colors are brighter on the nodes close to the cluster edges. To visualize this better, imagine traversing the ring and registering the highest cluster assignment value for each node. We would obtain a diagram like this, where we see that min-cut and daemon, they show a reduction in the highest cluster assignment value when they move from one cluster to the other. On the other hand, on the top, the red line show that TVGNN always have cluster assignments, since the highest cluster assignment is always at 1. To conclude, I briefly comment on the results on graph classification, where TVGNN is used to implement graph pooling. All the GNNs here have the same architecture, which is 2 blocks of message passing layer followed by a pooling layer plus a final readout at the end. The only difference is how the pooling layer is implemented, and that our model use GTV conv layers while the other models have GCN layers. The results are very favorable. TVGNN always perform equally or better compared to any other method. In particular, in 5 out of 9 datasets, the improvement in performance is statistically significant at 95% and even at 99% level. We have a GitHub repository with the code and additional material. The model TVGNN is implemented both in TensorFlow and in PyTorch and is currently available on the Spectral library. For any question, reach me by email or by Twitter.